There's this invisible code, almost like a genius shortcut, that's built right into the walls of every building you've ever set foot in. It's a system that keeps our world powered up, keeps us safe, and, believe it or not, makes it all surprisingly affordable. So today, we're going to pull back the curtain on the hidden world of electrical demand factors. But seriously, have you ever thought about that? If you went around and flipped on every single light, plugged in every phone, ran the oven, the microwave, the TV, the dishwasher, all at the exact same time, that's a massive amount of power. So how on earth do engineers plan for that? Why don't your breakers just immediately give up? Well, the short answer is they don't. They don't plan for that at all, because it would be unbelievably wasteful. Designing a building's electrical system for its absolute theoretical top-end load is just like this highway analogy. Can you imagine a 50-lane highway where most of the lanes are empty 99% of the time? It would be a colossal waste of money and materials. Okay, so if we're not building for 100% capacity, how do we build things safely? Well, this is where the National Electrical Code, you'll hear it called the NEC, comes in with a really clever solution. And this isn't just some boring old rulebook. It's more like a smart guide that's based on decades of real-world data about how we actually use electricity. The solution is this little thing called a demand factor, and you can basically think of it as a smart discount. The code knows it's extremely unlikely you're going to use every single thing at once, so it lets electricians calculate the system's needs based on a more realistic demanded load instead of the total potential load. And this isn't a guess, okay? It is a carefully calculated percentage that comes from tons of data. But here's what's so cool. The code is also smart enough to know when not to apply the discount. It has built-in exceptions. It knows that while you're probably not using every light in your house at once, a place like a giant hotel ballroom, well, that's a different story. For those places, nope, the smart discount is off the table. You have to plan for 100% usage. It's that kind of detail that makes the whole system work so well. All right, so how does all this theory actually translate to the wiring inside your own house? Well, the NEC breaks it down with some surprisingly simple logic, especially for homes. So here's the formula. Let's break it down. The code measures the load in something called volt-amperes, or VA. Don't worry about the term. It's just a technical way it can measure electrical power, pretty similar to watts. The code assumes you're going to use a certain baseline amount of power, so it says that first 3,000 VA of your home's lighting load gets counted at full price, 100%. But after that, the discount kicks in big time. The next huge chunk is only counted at 35% of its value. And for a really big house, anything over that is counted at just 25%. And here it is, you can see it right here, straight from the code itself. You can see that tiered system plain as day. This whole structure is what ensures your home is perfectly safe for everyday use, while also acknowledging the simple fact that you're almost never going to have everything on at once. This is the key to preventing that massive and expensive over-engineering. But of course, we don't use electricity the same way in every type of building, right? A house is not a warehouse, and a warehouse is definitely not a hotel. The NEC gets this, and so it applies different demand factors depending on what the building is actually used for. Let's just do a quick comparison, a house versus a big storage warehouse. In your house, lighting is scattered. You turn a light on here, a light off there, it's intermittent. But in a massive warehouse, it is super common to have huge sections of really powerful lights switched on for an entire 8 or 10-hour work shift. So the code adjusts. It says, for that warehouse, the 100% demand factor applies to a much bigger initial load, 12,500 volt amperes, before any discount starts. The rules are tailored to reality. And the impact of this is it's huge. Just look at this example. For a building with a total potential lighting load of 15,000 VA, you'd have to build for that full amount without a demand factor. But with the code's logic, a warehouse's calculated load drops to 13,750 VA. And for a house, it plummets down to just 7,200 VA. That's less than half. You can just imagine how much copper wire, conduit, and money is saved. So I know this might all seem like a bunch of technical jargon, but these demand factors have really tangible, real-world benefits for every single one of us. It really all comes down to 3 things: safety, efficiency, and money. First off, safety. By planning for realistic peaks instead of some theoretical maximum that'll never happen, we make sure our systems can handle what we actually throw at them without being dangerously overloaded. That reduces fire risk. Second, efficiency.
We save an enormous amount of copper, plastic, and other materials by not overbuilding everything. And finally, the economy of it all. Smaller wires, smaller conduits, smaller panels. That all means lower construction costs for builders. And those savings get passed on to the people who buy and live in these homes. It's just a smarter, safer, and a whole lot cheaper way to build.
And that really brings us to a final thought, a question for the future. These demand factors we've been talking about, they're all based on historical data of how we've used energy in the past. But our habits are changing, and they're changing fast. We have smart homes now, constant connectivity, and the big one, electric vehicle chargers, which pull a massive load. So the question we're left with is this: how will these absolutely crucial calculations need to adapt and evolve for the electrical future we are building right now?